In this video, I'm going to prove why for a simple harmonic motion, the let's say position function is going to be a sinusoidal function. So we start with Newton's second law of motion. So let's have this case. Let's say we had a spring, an ideal spring, and a block of a certain mass connected to that spring. Let's say that's the equilibrium position. And now I'm going to pull the spring a little bit to the right and release it. Then it's going to oscillate back and forth about its equilibrium position. So it will oscillate back and forth about its equilibrium position. At any position, let's say here, for instance, if the spring block system reaches this position, there will be the forces acting basically on this spring. F is equal to MA. The force acting here, it is a restoring force, right? The force will be backwards because the spring will try to restore back the block. So this is the restoring force. And we already know that the restoring force is opposite to the displacement. Since the displacement is to the right, so this restoring force is going to be minus K multiplied by X. It's opposite to the direction of the displacement, equals to the mass multiplied by the acceleration. It's simply the derivative of the velocity, and the velocity is the derivative of the position, so it will be second derivative of position with respect to t squared. Now let's arrange this equation. So you will have d2x by dt squared plus, so I divided by m basically, and I brought this one to that side, plus k over mx is equal to 0. This is what we call by second order differential equation in x. And if you look carefully at it, the function, so if you kept it as it was, let's say d2x by dt squared equals to minus k over mx. So the function whose second derivative will be the same as itself, it is a sine or cosine basically, because there is a minus sign. You are flipping the sign. So in this case, x is going to be some amplitude, a, cosine, and the quantity here, it's going to be radical k over mt. Okay, radical k over mt. Let's say at time 0 we started at this position, which I'm gonna call a. At time equals 0 I started at a, and at x equal a here, and here x is minus a. This is the x. So you want to check, you can check here, what is the first derivative for this one. So let's now write it here again. So just to make sure, x is going to be a cosine radical k over mt. The first derivative of x, so let's find the first derivative. So dx by dt, that will be the velocity, it's equal to a multiplied by this value, which is radical k over m. Derivative of cosine, okay, derivative of cosine, which is sine, basically negative, because the slope of cosine is downward. So it's negative a sine radical k over mt. All right, and do the derivative again. The second derivative of x, differentiate it again. So what will be the derivative of this one, of sine? We know the derivative of sine, it's going to be a cosine. So it's going to be minus a. You take this outside, the coefficient of t. So radical k over m multiplied by radical k over m, you will get simply k over m. Okay, k over m cosine radical k over mt. So if you look carefully at this one, clearly this quantity here, a multiplied by, so let's write it like that, minus k over m multiplied by a cosine radical k over mt. What is a cosine radical k over mt? It's simply x. So this one becomes, as expected, d2x by dt squared equal minus k over m, and this whole quantity here is x. Alright? So this means this is a solution for the motion, for this simple harmonic motion. That's why it's called simple harmonic motion, because that's the frequency W. It's one frequency. It oscillates with one frequency. And in order to get this oscillation, I should have a restoring force from the beginning. The condition was for a simple harmonic motion, there should be a restoring force which is simply opposite to the displacement. Okay, that was the condition. When we started with this condition, we reached this result, and that was the solution, which is a sinusoidal or a cosine or sine wave. So basically this is how the graph is going to look like, the x with respect to time. So at time 0, if I started from here, the spring will be at this location, then it returns back to the equilibrium, then it goes back to the minus a. It's simply a cosine wave, and so on. So it will oscillate back and forth with a frequency W which is equal to radical k over m, the angular frequency.